Hello. All right, so thanks for calling in. I'm still waiting confirmation from my pals over here that this thing is actually working. I'm a Twitch newbie, so please cut me some slack. Thanks for calling in. So I'm gonna give a quick overview of how Pulumi works. And so Luke Hoban gave a couple demos of a few sort of getting started and hello world examples to hopefully get a good idea of how, what Pulumi can do for you. I'll actually go through that just really quickly in case you missed those two. What I thought would be fun today, because Pulumi is actually open source, or will be soon, I thought it'd be fun to actually go through how Pulumi works. It's kind of a novel approach to an existing problem of how to express, cloud applications. We've taken a different approach than most of the technologies out there, and it's not, it's actually kind of a hard problem. So I thought it'd be fun to dive into how the engine works, the points of extensibility, and especially once we are open source, hopefully this will give you a sort of roadmap to the source code. So if you want to tinker or dive into different aspects of Pulumi, you'll have everything you need. So before getting into that, I'm just going to quickly go through an overview of what Pulumi does for you, and I'm going to show you two ends of the spectrum. I think you probably saw in Luke's demos that we handle infrastructure, serverless, containers, kind of the entire spectrum, because we believe really modern cloud applications are a combination of all of these things. I should mention, anybody who's following, who kind of follows me on Twitter or knows me from past lives, I'm really excited about Pulumi because I think every programmer and the future programming languages really is about programming the cloud. I did a lot with concurrency and asynchronous programming, working on await and C# and things like that. I think the next frontier is how people build cloud applications, because we're seeing a shift from thinking of infrastructure and application code as completely different things managed by different people, and I see sort of this grand unification to really have a platform for building distributed programs. Turns out it's a hard thing to accomplish, and I think after this talk you'll sort of understand some of the nuances of it. Like I said, I'll just show you a quick, getting started with Pulumi. I'll start with, I don't know how much Luke actually showed you some of these examples, but at the very low layer of the system, we have resource providers for all the different cloud vendors. So AWS, Azure, Google Cloud. We actually have Kubernetes support as well. At this layer, we're basically exposing every single property and every single resource for the target cloud as essentially a class. So you can allocate objects, and through the allocation of those objects, you're sort of expressing the infrastructure that you need for your application to run, and it kind of blurs the boundary between infrastructure configuration and app code. But at the very lowest layer, we've got super low level resources. So if you want to do like EC2 VMs, so this is a web server, it uses a security group and it's opening port 80. This is like very low level infrastructure code that is pretty common to see in CloudFormation or ARM templates or Terraform, for example. And in here we can we've got basically, it's not getting off to a good start. Let me show you a different example. So this example, that was a really low level sort of piece of code. And if I go now at the super high level, we'll see it's closer to what Luke was showing you last time, which is, okay, now we're programming in terms of cloud buckets and tasks that go ahead and use Docker files. And one of the coolest features that I think he probably showed is AWS Lambdas or Azure Functions or wherever you're deploying this to can actually just use Lambdas in your programming language. And so, how does that work? That's kind of neat. And we actually allow you to capture references to resources within your program. And so if you think of how people would normally express this code, I actually have a good example of a customer we worked with And I should mention, please do feel free to ask questions in the chat. I will happily answer them as I go. So this is kind of where a lot of our customers are coming from. So anybody who's done sort of infrastructure programming on AWS will be familiar probably with CloudFormation. And so if you look at this, what it's doing, CloudFormation basically declares a desired goal state for your cloud applications by saying, hey, here's a security role, here's a code pipeline thing, which is AWS's CI/CD system. And interestingly, you end up with things like, hey, here's a Lambda. And the way that the Lambda works is, there are a variety of ways of doing this, but sort of the default mode is to actually stick code inside of your YAML file. And so the unique thing about Pulumi is that you can just write code. And so if we go back to that other example, if I can find it, notice that we're just writing JavaScript lambdas, and Pulumi's runtime is sort of doing everything it needs to do to sort of take that, package it up, and upload it to the cloud as part of deploying your application. And obviously doing that requires some sort of novel language techniques. So I am going to go back and see if I can actually demo this one, because this is kind of interesting. Okay, so if we think about the fundamental concepts that Pulumi gives you, so let's break them down, right? So we just wrote a program, and that was the program I just saw you. So that's in just an ordinary JavaScript file, and we currently support JavaScript, TypeScript, Python, and Go. In fact, later in this talk, I'll show you the Go provider, which I kind of brought online last weekend. And it's kind of an interesting case study because it's one language provider, but it's fully extensible. So in the future, we can imagine C# and Java support, among other languages. Perhaps somebody will contribute Haskell or Lisp or something like that. Definitely Rust is something we've talked about. But the idea is that Pulumi programs can be written in essentially any language. And then we'll see later, the Pulumi runtime basically works in tandem with those language providers to understand the desired state of your cloud programs. And so, this is a program, it allocates objects, so new cloud bucket, that's actually just something we call a resource. And so the web server example we saw earlier, just resources. Here, cloud task, it's just a resource. And so resources are the fundamental sort of units that you're operating on inside of your programs. And the magic that we figured out is basically how to take those objects you're allocating at runtime and essentially map them to cloud resources that are actually the physical resources. And so when you look at CloudFormation or ARM or Terraform or any of these systems, what they basically do is they take your program, they evaluate it, and they figure out from that, okay, what are the set of operations I need to perform to make reality match the desired state expressed by this program. And so if you think about it concretely in terms of this one, just take this simple line. Well, when we run this program, it's going to allocate a bucket object. The bucket object will have some properties on it. This one, turns out, it just has a name, but you can see the cloud task here has a number of things. And so Pulumi will take that and basically build an object graph that represents the desired goal state, and then Pulumi understands what the current state is, and so it can actually diff the two of them, just like CloudFormation and some of these other tools, and then create a plan. And from the plan, it will figure out, okay, what do I need to do to actually make this match reality? So that's sort of it in a nutshell, sort of how the overall thing works, is put together, but there's obviously a lot of details that go into that. I should mention a few other just fundamental nouns that you're going to encounter. Stacks, I think Luke probably mentioned, stacks are essentially isolated instances of your Pulumi program. And so often a stack maps to an environment. So you might have, production, staging, development, testing. You might have production East Coast, production West Coast. You might have, a stack per customer if you're, a SI working with customers, or a SaaS product that's single tenants your product. Often people will stand up lots of stacks just to do testing, right? So maybe in a PR, you want to stand up a new stack that's a fresh instance of your application, run a barrage of tests against it, and use that to mark a PR green before somebody actually merges some changes. So stacks are super flexible. I can't get into all the different ways you can use them, but it's an important concept, especially when you're trying to understand how Pulumi works. In this case, I already have a stack stood up, and so just for fun, I'm going to go ahead and create a new one. So let's create a new stack. One thing I should mention that's maybe not obvious is the Pulumi CLI and everything you're seeing here is actually working in tandem with the Pulumi SaaS product to get the job done. So you'll notice that there are always, hyperlinks for things. So here, I can go look at this thing up on the website. And this is another important point in understanding how Pulumi works, because unlike some other tools that you run, you have to manage state files and worry about them getting out of sync, or whether it works in a team environment. Because the CLI just automatically works with the Pulumi service, it just works in a team environment. You don't have to worry about whether your state file is out of sync or not, and you could rapidly switch between these. So, I can go back to, the stack that I was just on. It's a fully qualified name, so I can go back to this, and now I can actually see, the stack resources inside of this guy. I can see, Pulumi config. So the config system is another key element of Pulumi that I think Luke probably already alluded to. So I'm going to switch back, and I'll just configure this just so you can see it in action. I'm just going to basically copy that same config. Notice that we're using Fargate to make all this a little bit easier. So Fargate is the new ECS infrastructure, so you can basically use containers as a service, not have to worry about managing your own clusters, which is great, especially for demos like this. So now if I run a Pulumi update, assuming I did everything correctly, which is a big assumption, you notice that it's doing a lot of stuff. So it's actually building the Docker container. You see the Docker build output here. So it built the Docker container. It allocated all these resource objects, right? So it, bucket, function, serverless function. And notice also there's a parent-child relationship between these. And that's an important part of the Pulumi programming model, so that we can basically create components that internally compose other resources. So notably, remember I was making a big deal earlier about what resources are? Well, each one of these is a resource. So these are all resources. Each resource has a parent pointer, and so that's how we are able to build the tree. If a resource does not explicitly have a parent, it automatically gets parented to this top level stack. And notice all of them have names. And importantly, Pulumi needs to basically be able to relate objects in your language runtime back to physical entities in the cloud. And to do that, we use names. And so the name is actually very important, and names generally need to be unique. And this is something we'll return to when we start looking at how some of this works. Another part to just note is, notice it says previewing. It actually hasn't done any updates yet. It's just showing me what would happen if I actually did a deployment. And this is really nice too, because this is where, we are infrastructure as code. We are immutable infrastructure in all the same ways that existing tools that you know and love are. We've just figured out how to bring general purpose programming languages into that space. And that's important because most language-oriented approaches that have come in the past just go out and mutate infrastructure. There's no audit trail of who changed what and when. It's ad hoc, so if something fails, you're failing in the middle of doing an operation. You can't typically preview what's going to happen. With Pulumi, we're actually giving you the full view of everything that's going to happen before we do a single thing. And so that, coupled with the fact that you get great IDE support, means that you're often finding issues much sooner, much faster in the dev inner loop, rather than finding them after trying to do a deployment and it failing 10 minutes in or something like that, which is a common thing that we hear with existing technologies. So I can go ahead and do the update. There's also this details, which gives me a full, complete, detailed diff view, and it's a lot of stuff. So, I can go through here. If I wanted to find out, let's take one of these just arbitrarily. So here's the S3 bucket. So somewhere deep down in this, it's actually going to create an S3 bucket. Well, here's the URN for that bucket. So I mentioned that everything is name-based. Well, we take the name that you gave us, and we actually concatenate that with some qualifying information, like the module it was declared in and the stack. This just helps to make sure that you're not worrying about names as much when you're creating resources in your program. There's a common thing with existing technologies where you have to somehow randomize the names or add some qualification to them, and you're constantly struggling with this. And because we have this model, it's much easier to stand up lots of different stacks without running into naming collisions and these sorts of things. And then we can see, the full set of information that is going to go into creating the AWS resource. But notably, we still haven't done anything. And I'm actually going to cancel out of this rather than waiting for it all to happen. I'm going to take a step back at this point. So, in fact, I'm probably going to switch to the whiteboard now just to help describe, because I think this is easier with pictures than it is with words. So if I've done this correctly, you now see a whiteboard. Here I am. Okay. So let's look at how the Pulumi system works at its core. So we've basically got what we'll call the engine. So we've got the Pulumi engine. So when you say Pulumi up, what's happening? Well, first of all the inputs to that are just normal programs, right? So you've got your program text, whether it's JavaScript, TypeScript, C#, it kind of doesn't matter to us at this stage. We're basically just going to run this program. And it basically has some metadata as well. So we've got this Pulumi file that tells us the language. So in this case, it will say Node.js. And then, of course, another input is the configuration. So you notice I set as configuration the region that I'm deploying into, whether I'm using Fargate, and a few things like that. And so we've got config. It's a very different config than the normal sort of YAML-based configs, Pulumi's config system. And we have secrets as well. So we have encrypted secrets as well to make it easy if you have, passwords or tokens or keys or things you don't want to be in the clear. We have first-class way of supporting those too. So, you can optionally encrypt your config also. So these form essentially the inputs for a Pulumi program. It's the program text, and it's really, to be honest, not the program text, depending on whether it's dynamic or statically compiled. So in Go, the input is actually a compiled binary. In JavaScript, of course, it's just text. If it's TypeScript, it would be still JavaScript because you first compile your TypeScript into JavaScript and then you give it to us. And so you take the program plus the config plus the metadata and we hand that to the Pulumi engine. Now what is the Pulumi engine going to do? Well, turns out the first thing it's going to do is it's going to say, okay, somebody just gave me a program written in this language. I need to do something with it. What am I going to do? So it does some minimal work to figure this out, but the main thing it does next is it goes ahead and loads up the appropriate language host. And so this is kind of interesting. So notice that the engine and the language host are actually fundamentally different things. been an interesting evolution building Pulumi. Just a fun fact. We started thinking we were going to do our own language. Then we realized, okay, we don't need to reinvent how people encode floating point numbers. And frankly, being able to leverage a package ecosystem is huge. I mean, I didn't even mention up here, but you've got infinite number of packages that you've reused when you're building your program. So then we moved to a model where the engine was monolithic and it just knew about JavaScript. And then we sort of had a breakthrough where we realized, no, actually we can tease out the language host into its own plugin and loosely couple the engine and the language host. And by doing this, we can actually support infinite numbers of languages. And so actually getting the interface between these was actually a critical breakthrough that we had at one point. And so here's sort of what's happening. I should probably move these down so I have a bit more room. So the engine talks through an interface, and I should mention the engine itself is written in Go. Just to reiterate, everything I'm talking about will be open source, and so you'll be able to see how this works. And if you're part of our private beta already, you should have access to all these repos. If you don't, shoot us an email, talk to us in Slack, we'll make sure you get access if you want to look around. So the engine is written in Go. We use, because Go is statically compiled, so we needed a way to dynamically load things. And so the interface for dynamically loaded plugins, we basically use gRPC and protobufs, which is a great technology from Google that allows you to basically describe an interface and have an efficient binary or HTTP2 interface into a component. And so we have this, little gRPC interface. It's actually surprisingly straightforward, deceptively so, and we'll look at it in a moment. But this is where the language providers basically implement out of process their functionality. And so that is communication going back and forth between the engine and the language host. We'll get into the details of how that works and this sort of thing momentarily, but as that's happening, the engine is learning new things. It's learning about the resources that are getting allocated by the program, and eventually what it's going to do in response to that is we have another point of extensibility for resources. So there are a few other points of extensibility. Those are the two main ones that if you wanted to come plug in, you could write your own language host, and Go took a couple weeks to bring up, so it's not like a Herculean effort to bring up a new language host. So if you want to contribute, we would love to have people partying on this. And I'll show you the PR for the Go language host. It's a good sort of blueprint. So the second point of extensibility also, over gRPC interface, is the resource providers. So these also, there's infinite numbers of these. The resource providers are what define essentially the resources that you can allocate and the logic required to provision them. So for the most part, this interface is actually create, read, update, delete operations for every resource you could possibly want to use. Whether that's AWS, Azure, Google Cloud, etc. So this likewise is pretty straightforward to implement, and we have a few different ways of doing that. And so stepping back, it's really, the engine is really the thing that kind of glues these things together, right? So the main things that the engine can do is, previews, and related to that, diffing. It can do updates, and destroys, which are basically the inverse of, well, let's just tearing everything down. Of course, it's got a notion of stacks. It's got config. Everything sort of that I already covered. Well, let's walk through sort of the main flow. So we do a Pulumi update. We're going to take the program. We're going to feed it into the engine. The engine's going to inspect the metadata and figure out what to do. It's going to first load the language host. And then it's going to start chugging away on the program, executing it. So at this point, the language host actually has spawned the program. And it's executing the same code that I showed earlier, new S3 bucket, let's say. So this is going to get communicated back to the engine over this RPC interface. And so what it's going to get communicated as is basically as a goal state. So we have, by virtue of having the type, we have basically an internal type token. You might have noticed this in the URNs that I showed earlier, but it will look something like, AWS colon S3 colon bucket. And so to get that, which is the type, we'll get the name. So we probably have maybe photos, and so we'll have photos in there. And then other resources, as you saw, have other properties, and so there's basically a property bag that will come along with this. And so the host is basically saying, hey, engine, here's a resource to allocate. During preview mode, it's kind of interesting because the language host needs to be prepared to do a form of speculative execution, because during preview mode, even though you've expressed you want a bucket, we actually haven't created the bucket yet. So what happens if you access one of its properties, like the domain name of the bucket that's going to be allocated by AWS? We can't possibly know that in advance. And so one of the, frankly, most complicated pieces of implementing a new language host is essentially you've got a DAG of resources, right? And so, maybe this is the S3 bucket, and maybe there are other things that depend on it. Maybe the S3 bucket depends on something else. So we have this notion of dependencies between resources that needs to be preserved. And so over here on the language side, we're just allocating objects, and generally speaking, and one thing you'll notice is every language does it slightly differently. The projection of the underlying resource object model differs by language so that it's idiomatic, right? So in Go, you have a little bit more fine-grained control over things. In Java, it will be much more class-oriented. TypeScript, we're leveraging union types and all these great, rich type system features. So every language sort of projects Pulumi in its own idiomatic way. And so it will have its own thing here. It turns out in JavaScript, we're using basically a variant of promises under the hood to maintain the data flow graph. In Go, we've got some channel thing. So the language sort of has its own view of the resource graph, and it may or may not actually need to reify that entire graph. And then once it gets communicated back to the engine creates that graph. And it has its own actual graph. It maintains the whole thing, and it needs to do that so that it can do parallelism, for example. So it needs to know the dependencies, the order in which it's safe to delete things. And what it'll do is, so during a preview, it just evaluates, and we basically simulate the data flow. During an update, we actually need to perform the update. And so the first time you run your program, it's going to be all creates, like you saw earlier. And so Pulumi will, in dependency order, basically do topological sort kind of thing and walk the graph, and then it will drive the resources. So what it'll see is like, oh, you need the AWS resource provider, we'll load that, we'll connect to it through gRPC, and then we'll feed it some create operation. So again, remember, this interface is mostly just CRUD. And so the creation is very simple. And as you can imagine, destroy is basically the reverse of that, right? It will walk the DAG in the reverse order and destroy things. You can't delete something while something else is still depending on it. So it is smart enough to do that, and also split parallelism on the delete where possible. And then update's probably the most interesting. Update, will actually diff states, and so it knows what the current state is. So maybe, I don't know, you've got some, let's say a Lambda, and it's got some code in it, and then you just update the text of the Lambda. Well, there might be some other resources, that depend on it, so on and so forth, but we don't want to update all the resources, right? We just want to update that one Lambda, that one piece of text that you actually changed. And so the engine knows how to basically take two graphs, pair the nodes within the graph, understand the edges so that it can do things in a safe way, and then do the minimal diff necessary to actually deploy your code. And so it'll just go patch the Lambda. The one line of code that you changed, it'll actually just kind of go do that. And as you can guess, probably by its name, the update operation is sort of what does that. So that was a whirlwind tour. There's probably a lot to cover in a small amount of time. I think I did want to just show a quick roadmap of the source code if you're in the private beta, you want to poke around, or if you're seeing this after we're open source. I think any number of these areas is something I could dive deeper into. Like, for example, I'd love to sometime in the future, go through what that gRPC interface looks like and how we actually create those. We've done some interesting stuff in the Kubernetes space to do some type generation out of the OpenAPI specs in Kubernetes, for example, so that we get perfectly full fidelity in the resources while getting great typing out of it. And then likewise, implementing a new language, it would be fun to maybe dive into how the Go language provider works at a low level. This hopefully gives you the overall top-down summary. Now I'm just going to jump back to the computer and switch my video. Okay. So I think I'm back here. I'm basically just going to give you a quick overview, and I'm going to spend maybe 10 minutes, let's say, because I know I'm a little bit over time here, going into sort of the structure of where some of these things live. So the main repo is Pulumi. That's sort of where most of the magic lives. That's sort of the, anything that's not out in a point of extensibility or in a box, this is where it lives. As I mentioned, it's written in Go, so let's use VS Code here to open it up. And so the CMD directory is basically the command line. So this is where, preview lives. So every command that you run with Pulumi, stack and init, everything, that lives here. What you often notice is things use engine and backend, and those are sort of two major packages. Because this is Go, you could program against the engine if you wanted to build new things out of it. It's, we have exported members, we've tried to architect it cleanly so that people can plug in and build new tools on top of us. And then you'll see in the package directory, we've got lots of good things. I'm not going to go too deep into this, I'm just giving you an overall structure. But, if you wanted to see how, for example, loading the language provider worked, you would go in here and, planning, this is all the magic for creating, previews and doing diffs and all that. You can kind of jump off from here. There's an SDK directory here, and an SDK contains basically all the language providers. So you see Go language provider, Node.js, Python. Because we dynamically load things, there's no need for language providers to actually live in this repo. You can define them anywhere. We just happen to define them here, so they're easy to find. It's conceivable later we'll move them out into different repos. And you'll see here, this is just a normal TypeScript project. Not really anything magic, but what you'll see is, the resource, the fundamental type that's doing everything you need with resources is actually just a class. And then it's going to go through this runtime, and basically this is where it connects up to the gRPC stuff that we talked about earlier, where basically this register resource thing, this will go through and do a bunch of gRPC things. So it'd be fun to look into how any of those things work, and again, Go and Python are right here alongside them. There's instructions on how to build from source if you want to play around there, which I encourage experimentation. The other top-level thing to note is the proto buffs that I mentioned, which are the points of extensibility, are actually just right here alongside the language providers. And so if you want to see what it would take to implement a new resource provider, here it is. Oh, sorry, not this one. This one. Here are the methods you need to implement. Configure, invoke, that's a separate thing that I didn't mention, but resource providers can have functions that you can invoke to do things like looking things up dynamically, which is kind of interesting. Check, diff, and then CRUD, just create, read, update, delete operations. Pretty straightforward. I'm not going to go too much into detail here. It'd be fun one time to go through what it takes to create a new resource provider. I will mention we have a bridge that effectively takes any Terraform provider and plugs it into this interface. And so you can use that. So if there's any Terraform provider out there that you really like, DigitalOcean is one that I hear of, for example. super easy to take that thing and just glue it up and get it into Pulumi right away. Other providers, like the Kubernetes provider, we wrote from scratch, but you can kind of go either direction there. So that's the Pulumi repo itself. And then what you'll find is for every major provider, AWS we've got here. And so AWS, this is the package provider for AWS. It turns out you probably don't need to touch the source code usually. You're just going to install a package. But if you want to, you can go look here. This one's generated from Terraform, like I mentioned. So that's actually controlled through this resources.go file. And what we're doing here is we're basically adding some nice module structure on top of the Terraform provider, which doesn't really have as much of that sort of user-friendly metadata. And so all of the, you'll see the Azure resource provider has effectively the same thing going on. Google Cloud provider, also same thing. Kubernetes, you mentioned, is very different. That's actually got, a lot more to it. So you've got, this whole open API based code gen and a lot of fun stuff there. And that's most of the main top level repos. There's also, examples and a bunch of scaffolding stuff. The only major parts I'll mention are packages. So resource providers are sort of, think of those as the low level things that provision cloud resources. You can create ordinary packages that they're just code, right? They're not Go plugins or anything like that. They're just packages, right? And so we have a few of those, like the AWS Infra package. This essentially just has some components that are just make it easier to program against AWS infrastructure. So for example, I'll look at the example here because it really pops when you see it. So if I want to provision an AWS infrastructure, AWS network that's in a VPC that's got properly subnetted, multi-availability zone networks, subnets, public-private subnets, I can just do this as a consumer of this package. And all this package is, this AWS Infra package, is code, TypeScript and JavaScript code. It's not, you don't need a Go plugin or anything like that. And so I can go look at the implementation of this here, and it's pretty complex, right? Because setting up an AWS infrastructure is complex, but that's the idea of having these components is you can take that complexity and put it underneath a simple and easy to use interface. And so you notice it accepts all these args for controlling various aspects of how the network's going to be set up. But internally, it's kind of fun to walk through this because it's really not doing anything you couldn't build yourself, right? So we'll notice, let me just find an example. So here we see new EC2 VPC, right? As I mentioned earlier, this is just a Pulumi program, and it's turtles all the way down. So it's just creating a resource, and that resource works the same way I showed you on the whiteboard. So if the definition of AWS Infra changed, maybe this changed to false, let's say, next time we ingest that package and run a Pulumi preview, we're going to see that as a diff. In the same way the resource graph works that I showed on the whiteboard. And so you can build these complex abstractions out of lots of little pieces. And so that's sort of the magic of some of what we've done. And then the cloud package is another one that sort of works the same way. It's a little bit more complicated. You've probably seen, we've got a service type which does Docker builds, where you can have a container that's built out of an image. And so the Pulumi cloud package is probably our most sophisticated, pure library that isn't backed by a Go plugin or provider. And so that one's a lot of fun to spelunk in. Our intention is that's going to be multi-cloud. Right now, we only have the AWS implementation. So if you're looking for areas to hack and play around with, getting a service up and running on Azure is definitely something that's on our short-term horizon, and it's definitely areas of possible contribution for open source that we'd definitely welcome. So I think I probably tried to cover too much ground, but I hope it was fun and exciting. And I think, probably we should do regular deep dives, maybe every 3 other episodes or something, so we can keep double clicking into some of these areas. Definitely curious to hear what people are interested in. Either leaving feedback on Twitter, here in the Twitch chat, in Slack, wherever you can find us. Love to hear from you. So I hope you had some fun. Thanks for joining. See you next time.